I'd like to spend some time reviewing the concept of half-life, especially how half-life applied to your M&MEM lab. During that lab, hopefully you notice that each shake should have represented a half-life, because you have a 50-50 chance of the M on the M&M landing up or down. A couple questions that we struggled with during that activity was, can you predict when a specific M&M will decay? Where you can predict approximately how many M&Ms will decay, you cannot, with 100% certainty, point at one M&M and say, I know that one's going to decay the next time I shake this. It's a totally random event, like drawing a certain card from a deck or a lightning strike. Completely random events. Also, how could we modify this activity to demonstrate that different isotopes of an atom have different half-lives? Okay, what we'd have to do here is use an object that doesn't have a 50-50 chance of decaying. A good example would be a common six-sided dice. I'd like to work through an example of a half-life problem using six-sided dice. I have 100 six-sided dice representing my radioactive isotope. We're going to say any time that a 1 is rolled, that this isotope decays into something that's stable. I also colored the 1 red so it'd be easier to see. Something I'm going to do that's different than the M&MEM lab is every time one of these decays, I'm going to replace it with a stable isotope. So this decays into something stable that's not going to decay. I'm going to represent that with a marble. So before you watch the simulation, I would like you to make a prediction about how many dice do you think I'm going to remove after that first roll. So how many of the 100 dice do you think first time I roll it are going to be ones up? Also, I want you to predict how many rolls is it going to take me to get to 50 dice, which would be one half-life. Because I don't have a 50-50 chance here, so it's going to take more than one roll, or it should take more than one roll. So pause the video and make these predictions before you continue with the next part of the video. So as you can see, I started with 100 dice. After this first shake, I removed any dice that were one up, or red side up. On this trial, I happened to remove 14 dice. I did this lab 3 times, and on average, each time the first roll occurred, I removed 14 dice. So I replaced those 14 dice with these glass marbles, and I kept repeating the procedure, shaking, taking out the dice that had a 1 or red side up, replacing them with a marble, which represents the stable isotope, the isotope that is no longer decaying. I keep doing this until I run out of dice, or I did 30 shakes. Like I said, I did this 3 times, and I'm going to show you a graph of my data that averages how many dice I removed after each shake for 30 shakes. Right, so let's look at that prediction for how many dice should be removed after the first roll. If you have a 6-sided dice, you have a 1 in 6 chance of rolling a 1. So if you have 100 dice and a 1 out of 6 chance of rolling a 1, you take 100 times that chance, 1/6. This should get you about 16.7 dice should be one side up after that first roll. So 16 or 17 dice. I had an average of 14 dice with the one side up after that first roll, so kind of close. How about the half-life for our 6-sided dice? Well, here's the graph I was able to create by doing this lab for 3 trials. If I want to find the half-life, I can read the graph. I started with 100 dice, so half of 100 dice is 50 dice. So if I make a line from 50 over to where the graph is, and then I read down to the x-axis, I can see that happens at about 4.5 shakes. All right, well, let's try to get an average. Okay, half of 50 is 25. So how many more shakes did it take to go from 50 dice to 25 dice? Well, same thing. I start at 25, I make a line over to where my graph intercepts, and that's about 8.5 shakes total. Well, it took me 4.5 to get to one half-life, and another 4 then to get to my second half-life. So right now I have 4.5 shakes, 4 shakes. Let's do one more. Half of 25 is 12.5. If I do the same thing, go to 12.5 dice remaining, read over to where it intercepts my graph, that's about 11.5 shakes. Well, I was at 8.5 shakes, now I'm at 11.5 shakes. That's 3 shakes. If I average those 3 half-lives together, 4.5 plus 4 plus 3, if I average those together, I get a half-life of about 3.8 shakes. So it should take around 4 shakes to get to the half-life. The actual value is actually 3.8 shakes. So I'd say we did a pretty good job. Now, I hope this helps you understand half-life problems and using a graph to determine the half-life a little bit better.